All right, everyone, thank you for your patience. So my name is Sean Devine. I'm the rental coordinator for ITM Instruments, and thank you for joining us today on this webinar via ITM University. Today's topic is facilities maintenance, realizing cost savings through proactive maintenance and energy savings with Fluke. We kindly ask for the duration of the webinar that you mute your microphone. Our presentation will last about 40 to 45 minutes, and then at the end, we're going to have time for some Q&A. So you can ask questions at any time. Simply use the chat feature, and we'll get to your questions at the end during the Q&A period. ITM Instruments has been working closely with Fluke for many years. We pride ourselves on being a leading distributor of Fluke, and this is a result of our dedication to offering you our product expertise, service, and competitive pricing. All right, let's get started. Today's webinar is presented by Dave Robley from Fluke. Dave has been with Fluke since 1984, recommending test equipment solutions for customer applications relating to thermal imaging, vibration testing, power quality, electrical measurement safety, and motor drive troubleshooting. Dave has a level 1 certification in both infrared thermography and vibration analysis. Dave also holds a BSE from Marquette University and currently works as a sales applications manager based in the Chicago area. Thank you, Dave, for taking the time today, and it's all yours. Thank you.
Thanks, Sean. Appreciate that. Thanks, everybody, for inviting us in virtually. As Sean mentioned, we're going to be really looking at cost savings today. First, via proactive maintenance practices, and then we'll be looking at an aspect of energy savings. So, as you mentioned, we're going to be kind of splitting that time up, 25 minutes or so. We'll be looking at proactive maintenance, and then maybe the balance of that, looking into the topic of energy savings via leak detection with an exciting new technology called acoustic imaging. So let's move forward. And we'll start with the maintenance practices. I think most, if not all of you on the call realize that it pays to be proactive from a maintenance strategy rather than just waiting for equipment to fail and then performing reactive or breakdown maintenance. We do have some numbers there below relating to rotating machinery, motors, pumps, compressors, some of the examples of cost savings from being reactive to predictive. Pretty big savings, and not just along the lines of downtime, but also lower maintenance costs, decrease in breakdowns, equipment failures. Let's take a look at that from maybe a more real world dollar example. So let's say you have 100 motors in your facility. Average of horsepower across all those motors is 50 horse. From a maintenance cost savings, that would translate to about $40,000 annual in being more predictive or proactive versus reactive. And then from a downtime perspective, let's say your plant has 16 hours of downtime per year. It's costing you $10,000 an hour. That would represent 160K worth of loss from downtime. And looking in the middle there, of the reduction in downtime, say 40%, that would be close to 65K savings annually. So it pays to be proactive. That's the message there. But there's some challenges, that maintenance personnel face. So we'll kind of look at what some of those challenges are. We'll lay them out here, but then we'll go through that in a little bit more detail. So there, as you all know, there's changing factors there in the workforce. Maintenance managers are having to do more with less. What they're working on tends to be getting more complex, not less. So and downtime is more critical now than ever. Also, there is a change in the workforce. A lot of the people that have a lot of on-site tribal knowledge and plant experience are now moving on to retirement. And so there's a little bit of a, not necessarily a knowledge gap, but really more of a an on-site experience gap in knowing their assets. From a knowledge standpoint, you might be in a position as in the bullet there. Why are we doing the same work over and over and over? Why do our assets seem to be failing in the same way? And where do we start? What tools do we use? And then how do we justify those tools? Maintenance people, of course, want to get tools that'll help them do their jobs, but how do you justify the cost of investments in the tools? What's the payback? And then finally, how do we get started? I think many companies have started or tried and failed to implement wide sweeping predictive maintenance programs. And we'll be discussing a strategy in order to start small and to not run into those pitfalls that have caused programs to fail in the past. So we're going to look at the concept of tiered maintenance. And maintenance teams now have to choose, well, we only have so many assets, so much time. Do we either cover only the critical machines or cover things less frequently? How do we really approach the challenges that we have? The medical industry has actually addressed a similar type of a problem, and I'm going to introduce the concept of screening versus diagnosis. So if we look over at the diagram here, all patients are important. So if you look at patients as assets from a healthcare standpoint, you want to screen everybody. So at this level, you have knowledgeable people that can make health measurements, health assessments, and in many cases solve the problem. If not, then perhaps you need to move up to more of a diagnostic level. And oftentimes then at this level, you can solve the issue, address the issue, fix it, and then the person goes on their way. And then escalate to specialists as is needed. So if you really look at that and try to do that from a maintenance standpoint, we're recommending the same type of approach, is really screen assets with intelligent tools for potential problems. So you screen everything, or at least everything that is worth screening. It's not just a direct replacement, but you want to screen assets with some technologies that we'll be looking into. And then for problems that are more critical or assets that are more critical, then we'll diagnose those. And then in some cases for the ultra critical machines or very complex machines, then there would be more expert analysis needed. So kind of keep in mind that screening versus diagnosing approach. So some of the benefits of doing that are, don't analyze everything. Don't spend time analyzing healthy machines. Screen, do health measurements on machines, and then that will reduce the amount of work, make the best use of the assets that you do have. So again, keep in mind this tiered approach: screen, then diagnose, then refer complex problems on complex machines perhaps to experts. This is another example of what are some of the assets that we might be looking at here. So maybe at the bottom you might have a lot of motors that are not as vital, maybe still worth screening, to catch a failure before you have downtime, but not as critical as assets that are in the middle tier or at the top tier. One thing that we'd recommend is that, and we'll refer back to this, but it's a concept of a criticality survey. Look at your assets, which are the most impactful if they go down, and it's not necessarily by size, but by impact or downtime. Look at the typical failure modes that they've exhibited. Use some of your plant experience to know that we typically have mechanical failures on these assets versus electrical, but also note by asset what typical failure modes might be. On root cause of failure, oftentimes people keep fixing the same things over and over. For example, on pumps, bearings, and seals. So you're getting things back up and running, but you keep having the same problems over and over. So oftentimes it helps to get to the root cause, not just find the symptoms and fix something just to have the same problem back up. One example would be, for example, bearings and seals on pumps. A lot of times people think that on coupled machines, if you have a flexible coupling between a motor and a pump, that that will solve any issues or mitigate anything related to misalignment. While it's true it won't physically damage the machine, it won't fly apart, misalignment, those forces are still present and they're transferred to the bearings and the seals. So if you are seeing this type of failure mode, perhaps it's related to misalignment, and especially so if you don't have a formal misalignment program on site. So in this case, it might be worthwhile having a diagnostic type of approach, not just screening. We have too much vibration, we have bearing issues, but why do we have too much vibration? In this case, misalignment. And then if alignment is an issue on a lot of your machines, you're seeing this failure mode, maybe it makes sense to look into or investigate a formal alignment program. So let's take a look at an example and some types of measurements that you might need to make. So again, we recommend screening assets, find which ones are good or bad. You might have 500 assets or more in a plant. So it would be good to be able to make some quick screening measurements with a variety of different tools, which we'll cover in a little bit, but determine, which ones are healthy, which ones are not healthy. Let's narrow down from that 500 to the 25 or 30 or so that really need the attention. So screen, read and trend. You can save health measurements using our Fluke Connect app, which we'll be covering a little bit later. But essentially, health measurements can automatically be saved without needing to resort to using a clipboard and saved to a cloud database. Next, for machines that are more critical or that warrant a diagnostic approach to get to root cause, approach that with diagnosis. And that we show an example of vibration and infrared testers there. So in this case, as it's highlighted, let's say misalignment is a root cause and you also see that you have bearing wear. It's good to be able to get to that root cause and then take corrective action with laser shaft alignment in this case. And then once something is fixed and put back into service, check, make sure that the repair is good and you can get back up and running. There's three pillars that we're going to examine as far as success in a program, and we'll also briefly look at why some programs fail. For example, a new proactive or preventative or predictive maintenance setup. Number one problem and the number one killer of predictive maintenance programs is you start too big and you never really get it off the ground. It's just too much from a software standpoint, from a data gathering standpoint. So what we're advocating here is start small, start simple, grow, have some successes. One of the successes, or how it's measured, of course, is cost savings. So if you're able to look at and find cost avoidance by minimizing or avoiding a downtime event, you can translate that directly to dollars. If we would have had this event occur, this would have been a maybe a $20,000 incident. So that'd be a good example of cost avoidance. So it starts with, again, that criticality survey of your assets. Along the ways, then select technology tools that might match the failure modes on the instruments or on your assets. Next is the tools. What type of tool should we use? And generally the best approach is with a mix of different type of tools, not just one tool to measure everything, but we're going to examine how electrical measurements combined with infrared, combined with vibration, can actually be a much better, more effective approach to determining health. And then finally, what do we do with the data? We don't just want to capture data for data's sake. We want the data to work for us. We need answers from the data, but we want to be able to gather it easily and quickly. So wirelessly enabled tools can help with that activity. And we'll be covering the Fluke Connect app in a little bit further detail, as well as the different types of tools and technologies. This is the potential failure curve. I think many of you have seen this, but essentially it shows a life cycle of a machine from when it's put into service to when it eventually fails. And one of the things that we see along the way as equipment gets older and goes further down this life cycle, it tends to waste more energy and it becomes much more expensive to repair. So it would make sense if we can make some health measurements along the way, and if we can, if not predict when something is going to fail, predict the likelihood of something failing, then you could address and you can allocate your maintenance resources and efforts in those directions. There's a number of different types of technologies or measurements that can be made on assets to determine the health and again, likelihood that something might be failing, and again, get out ahead of breakdowns. So we're going to be examining specifically thermography, electrical, and vibration. That's why they're highlighted there. But each of those technologies have advantages. They can offer some basic information or advanced information depending on the users. And different assets might require a mix, might require more than one type of technology. For example, thermal imaging, it's a great place to start. That might be a great screening approach on a lot of assets, but it's not going to tell us necessarily why something is overheating. But again, it's going to point out that this is overheating. You need to make some additional measurements on this asset. Most of you are probably familiar with thermography, thermal imagers, infrared cameras, but essentially they're devices that allow you to see heat. Heat can tell us a lot about asset health, whether something is healthy or not. So keep in mind that they measure, they're temperature measurement devices, and they take the measurements and then create images based on heat that's being emitted from assets. Thermography is pretty easy to do. So it's very easy to take pictures, capture images. You can take those images and then your knowledge of your environment, that can tell you a lot about whether something is healthy or is not healthy. It is not as easy to interpret images. So that might take some training, some experience. There are some different methods that we'll examine or different approaches to using thermography on site, again, with the thought of being more proactive. And keep in mind that it could be used for screening and also for diagnosis, depending on the situation. We'll take a look at a few different application pictures. I think a lot of you have seen things like that. Thermography is great for electrical. It can help point out things like imbalanced, unbalanced loads, as would be in the lower right corner. Examples of single phasing, which would be maybe the upper right there, or loose hot connections. But they can tell you a lot and be fairly diagnostic if you understand what can be generating the heat. But again, it's a line of sight technology, easy to use, fast, non-contact, and it makes a great screening tool for electrical applications. You can also use it in more the mechanical type of application, as is evidenced by roller bearings on the lower left, pillow block bearing on the upper left, coupling bearings on the upper right, and even in heat exchangers, other types of mechanical systems. But you can use this as a screening tool. One example might be you have overhead conveyors, small conveyor motors. They might be small, but they're very critical to your operation. Thermography can make a great screening tool at a distance that you don't need to get a man lift or some other type of device to be able to get up and make close-up measurements. So again, you can screen perhaps by heat, which of the motors are much hotter than other ones under similar load. Here's a few different ways that people tend to use thermography on site. Especially in mechanical, where it's a little less definitive as far as the images. How hot should a bearing be, for example? Well, the answer is you don't really know, so it makes sense to perhaps, if something is new, capture baseline images and temperatures. Or if things aren't new, at least get a starting point from where you're at. And then you can look over time to see if there are any changes that might jump out. Another good approach is comparative. Let's say you have multiple motors, pumps, all under similar conditions, similar loads. You can compare between assets to see if there's anything there that jumps out. For example, between the center, left, and right images. You don't know exactly what the temperatures maybe should be there, but you do know that it looks like the bearings on the right are hotter than the ones on the left. And so that asset deserves further attention. So again, you're screening, you're narrowing down with that comparative approach. From a trending approach, if you actually capture images and then take measurements on them, you can put temperature markers, and actually you can trend that hotspot over time to be able to determine when we need to take action and do a deeper dive into what the problem is with that asset. And of course, thermography has a lot of other applications on site. We're not going to be addressing those here, but they can be critical when it comes to reducing downtime in processes, operations, variety of other applications on site. Now, keep in mind that thermography is a line of sight type of technology. So you do need line of sight to what you're seeing. If you are working on certainly medium voltage applications, switchgear, high energy applications, it might make sense to investigate or look into installing infrared inspection windows. They allow infrared energy to pass through them. And if you put a camera up to them, you can essentially see what is going on behind the panel. So it enables you to work much more safely in high energy environments. Next, we'll take a look at some of the electrical type of measurements that can be used to, and the types of tools that can be used to, again, determine asset health. All assets in a facility rely on adequate electrical power. So it makes sense to be able to rule in or rule out power or voltage supply to your assets in order to determine are there problems, are there downtime issues here, are there things that we can correct to fix our problems, to ensure reliable operation. There are tools now, handheld tools, that not only can make power measurements, electrical power measurements, but they can also derive torque and speed from the electrical measurement to be able to determine mechanical efficiency, and then to examine things that might affect motor life, for example, looking for mechanical overloads, unbalance, distortion, all things that can cause additional heating and shorten the life of the motor. The lower screen there actually shows on a dashboard sort of format where you can actually feed NEMA nameplate information into the motor analysis portion of the tester, and then you can determine, am I running this motor in an overload condition? And then that might point you to further diagnostic in the drivetrain. Why do we have that overload occurring? So that might be something, again, to ensure motor health, to make periodic measurements through the electrical connection to be able to look at and assess mechanical performance as well. VFDs are at the heart of many companies' assets, so it makes sense to be able to troubleshoot them quickly if you have to react and if they go down, but also perhaps baseline or capture known good information, as is evidenced by the screens above on VFD assets, and then also to be able to save that so that you know what good looks like for comparative testing. A tool called a motor drive analyzer helps automate that process. Most customers are not VFD experts. And what this tool does is provides a simple, easy, menu-driven interface as to what measurements to make on drives, where to make them. It will show you images on how to hook up probes. It will automatically set itself up to make the proper measurements and then allow you to save those measurements for documentation purposes. So it is essentially a guided setup and guided usage of the tool to help speed that up and also to be more proactive so that if you do have an issue, you can do some quick comparative testing to a baseline. Insulation resistance testing, that's another area in which you might be using this type of tool, but maybe not in a proactive fashion. A lot of people use insulation resistance testers or megometers when they have a motor issue or a motor failure, a breaker trip, motor overheating. They will actually do an insulation resistance test to see, is my insulation on the windings breaking down or not? Well, you can also use this proactively over time when you take motors offline to look at and trend that insulation over time and look for evidence of a knee in the curve or a drop off to be able to more predict when it might be good to either take this motor out of service, have it replaced, or have it rewound. Next, we'll take a look at vibration. And again, keep in mind that screening, diagnostic, and corrective approach, and then verify that we had talked about before. We're going to look at two route-based tools or tools that people would take out into areas of the plants or on a route and then make measurements. The 805 FC vibration meter, kind of think of it as that nurse, going back to the healthcare analogy. It screens and it makes intelligent measurements on bearings, on overall vibration, and bearing temperature. And those measurements can easily be saved automatically in the Fluke Connect app. They can be looked at over time, or you can use that as a red flag that there's an issue here. And if the asset is critical enough, then it makes sense maybe to bring in the doctor, which is the 810 vibration tester. It actually can see the same types of problems, from an overall vibration and bearing issue standpoint. However, it can get to that root cause, that misalignment, looseness, imbalance, bearing wear. So you might see bearing wear, but it will also call out faults, for example, for misalignment, if that's the root cause. And you can trend faults over time. So maybe you see that you have a moderate type of a fault. It might make sense over time to look and see, well, how quickly is that moderate bearing fault getting worse, for example. And then, of course, depending on the type of issue, laser shaft alignment is a great approach to dealing with misalignment. Misalignment tends to be about 50% of the vibration related issues in coupled machines tends to be from misalignment. So laser shaft alignment program might be a very good approach if this is something that you're seeing. in terms of bearing failures or pump seal failures. This is also a guided tool, helps guide you very easily through the alignment process. And as you can see in the image, also shows you that there are corrective actions that you can take. For example, for vertical alignment, it's very prescriptive. Tells you that you need a certain amount of mils of shims to add both to the front feet and the back feet in this case to help correct alignment. So there are tools out there that are guided, that are very straightforward to use. Next, we're going to look at Fluke Connect. And Fluke Connect is a platform that enables the use of wirelessly enabled tools, electrical, vibration, and infrared, and they have the measurements from the tools automatically go to the cloud, and if you want to, you can actually associate that with assets by asset names. So we'll look at that a little bit further. We have some, for example, examples of infrared, vibration screening, and insulation resistance testing. Technicians on the plant floor can make measurements, automatically save them via the Fluke Connect mobile app to the cloud, and then that can be used to generate work orders, to look at asset health over time, asset management. So again, you can start as small as you want or get as big as you want via this approach. So in short, it pays to be proactive. We looked at a lot of different aspects: maintenance cost savings for minimizing downtime, extending equipment life. And we looked at the screen, diagnose, fix approach, a tiered maintenance approach. Use that criticality survey in your assets. Determine what's the best approach. Perhaps screen everything, diagnose where it makes sense. Really narrow down from all of your assets to the ones that need the attention, diagnose those, and that'll help make the best of your minimal or minimum maintenance resources that you have to work with. Match technologies and tools to the failure modes. We looked at 3 examples: thermal or infrared, electrical, and then also mechanical or vibration, to those assets and the types of failure modes that they tend to exhibit. Save data, look at equipment health, assets over time. Start small. Again, document cost savings or cost avoidance. That will help provide funding for further investments into maybe more tools and growing your proactive maintenance program. Well, now we're going to move on into the energy savings portion and look at an exciting new technology called acoustic imaging and how that relates to saving energy. We're going to focus on leak detection in compressed air systems primarily, but not just compressed air, but we're going to be looking at really compressed air systems because they tend to be a big waste of energy, and you can realize significant cost savings. So the electrical, or I should say the EPA, or at least in the U.S., they've done some studies on really cost waste from compressed air systems. A typical plant that doesn't have a leak maintenance program loses about 20 to 30% of your total compressed air output from your compressors. So if you look at that another way, they're running 20 to 30% longer and harder than what they need to. So let's say you have a plant that's got either a 200 horse compressor or it actually maybe it could be multiple compressors, total 200 horsepower. They're running 24/7 all year long. Let's say you have a base electrical rate, 8 cents a kilowatt hour. It'll cost around $90,000 or so to operate those compressors annually. So if you look at that as being 20 to 30% waste, that could be in the over 25% or 25K wasted energy cost annually. Pretty significant. So that's a big opportunity for cost savings. It's also shown that if you have a proactive leak detection and repair program, you can cut that 25 to 30% down to less than 10%. So it makes sense. Compressed air leaks are expensive. It's a recurrent problem. I've been told it's much like weeds in the garden, where once you fix them, you're not done. You need to do periodic inspections, as leaks will reoccur. So it's a proactive activity. So in addition to energy costs, there can be also other impacts, safety impacts in some case, perhaps production impacts, product quality impacts. It can also shorten the life of your compressor package. I'm going to run a quick video, and this is a video that we normally have online at fluke.com. If you bear with me, we found that we have some audio issues when trying to run videos on our presentation platform. So if you'll indulge me, I'll actually narrate this. We count on air for a lot of important things. Compressed air is everywhere. We don't always think of the pain leaks cause. Leaks can stop us in our tracks. What could you repair if you had an easy way to pinpoint a leak, even from a distance, and save money? If you rely on compressed air, you can now forget the old, slow, and possibly messy way. The new Fluke Acoustic Imagers use patented sound sight technology to visualize leaks. Enhanced scans can clearly see leaks you can't even hear. The Fluke II900 and II910 acoustic imagers work in noisy environments without needing to shut down the line. Scan large areas quickly so you can find leaks much faster and improve your bottom line. So let's take a little bit more of a dive into, well, what really is acoustic imaging and how does this really apply to leaks? The concept is, and some of you may actually have experience, any type of pressurized gas, whether it's air or other gases, that leaks or escapes through an orifice will emit noise up in the ultrasonic range. And in the past, there are tools that can listen up in the ultrasonic range to be able to hear leaks with the thought of trying to detect and then locate them. So acoustic imaging is based on ultrasonic. And what the technology does is it does listen up in the ultrasonic range, but the technology in the tool allows for actual mapping or visualization of leaks on a camera display, as is shown there on the right. But it's based on ultrasonic, and leaks are detected and then located and then overlaid on a visible image. So keep that in mind as to the basis of what the tester does. So as we mentioned, it's for primarily finding leaks, and that could be in compressed air systems. It can also be not just pressurized leaks, but vacuum leaks. Could also be other types of gases. Could be high pressure steam. That might be a safety consideration. But other gases that you as a company might need to pay for, such as welding gases, argon, nitrogen, oxygen, hydrogen, CO2, and even natural gas. We'll take a look at some example images taken with acoustic imaging of a variety of gases at a later slide. Acoustic imaging is easy, so it enables anyone to visualize where leaks are very quickly, right out of the box, no extensive training nor experience needed. And you can use it anytime because it's visual. You can spot leaks at a distance. That's the detection part. when a plant is up and running. So you don't have to wait until the weekend or downtime to have somebody walk around and listen for leaks and use older methods such as soap and water based on listening to find leaks. So no more waiting for shutdowns. Let's take a little bit closer look at how typically people have been using ultrasonic tools. If we look up on the top box here, there are ultrasonic tools, and you can't see it here, but it's a handheld tool, perhaps with a wand or parabolic antenna that can focus the ultrasonic information, feed it into the tool, which translates the ultrasonic down into an audible range that the operator can hear. So this operator is actually listening and trying to interpret what they're hearing to determine, is this a leak or is this something else? So that interpretation is important. It requires experience, training, and certifications. Not only that, typically, rather than inspect from greater distances, you have to actually move up very close to all the fittings, all the connections, hoses, etc., and make close-up measurements and then interpret. So it's meticulous, it's very slow. And then typically you would tag the leak, write down its location, and then move on. With acoustic imaging, you can start from a great distance away. So if you keep these two terms in mind, detect and locate, that's really the power of acoustic imaging. You can detect at a great distance. So if you see something, you can actually move then much closer to it and then pinpoint the actual leak source much more quickly. So rather than taking 10, 20, 30 minutes to track down one leak, you can find multiple leaks in minutes without that training, without that experience. And then you can save that in a camera. You can create documents, reports that can be used to go and fix leaks. Another challenge that I'll point out here is that leaks, just like any type of sound, it's emitted in all directions and it bounces off the surfaces. So oftentimes people in this environment might be tracking down what's called a reflection or noise bouncing off of a surface. Using the acoustic imager, you can very easily sort between what's a leak and what's a reflection. So if you see something like this, all you need to do is move to the left, move to the right. A leak source will stay in the same spot and be constant. A reflection will move as you move or perhaps disappear. So again, armed with some user tips, almost anybody could use acoustic imaging effectively, quickly to find leaks. So how do we do that? So if we look at this is actually an array of ultrasonic sensors, specially arranged that picks up ultrasonic information. As sounds are emitted, it will actually strike the different microphones at slightly different times. And through processing in the unit, that's how we're able to not only detect, but more importantly, locate where that is and visually map it on the display. Here's some example images that we'll run through of a variety of different types of leaks, different environments. Keep in mind that all of these are from running plants, some cases very, very noisy. So the product is very effective at mapping leaks, even in presence of high ambient noise. One example of that is over here in the exhaust leak. This would represent sound level or ambient noise down in the audible range. The tester can effectively ignore all that and only map what is in this range here. And it is a touchscreen operated tool, so it's very intuitive to move this around up and down to best be able to pinpoint leaks in a wide variety of applications. This is something over here, the overhead air, that's noteworthy because you didn't have to get a ladder or a man lift or fall protection to be able to get up close to that leak, you could identify it quickly and safely from the ground. Moving on to some other examples of other gases. The technology is for detection is really gas independent. Different gases might be more or less noisy, I'll put it, than others, but still the concept of detecting and locating can be used in a wide variety of gases. As I mentioned, CO2, welding gases, argon, nitrogen, natural gas. We have a variety of examples there, all in different environments. Some of them were taken in steel mill environments, such as the furnace gas, the natural gas, hydrogen were ones that I took myself at a pretty noisy steel mill. The technology also can lend itself. We have two models, the II-900 and the 910. The 910 can also detect an electrical phenomena called partial discharge, which could lead to an out-and-out failure in high energy equipment, particularly medium voltage levels or high voltage levels. So at substations or medium voltage switchgear, medium voltage equipment, partial discharge is a phenomena which is a partial arc or maybe the beginnings of a breakdown of insulation, and it's actually small arcing that is occurring, as is evidenced by the two pictures here. So if this is something that you would want to know about, certainly, so you could perhaps take measures to bring that offline when you can and affect repairs versus waiting for a catastrophic failure. And this is another example at perhaps a substation or high voltage transmission line. So the technology works. It picks up things up in the ultrasonic range that can be either leaks or an electrical phenomena, if that is something that would be of use at your particular facility. We're going to take a quick look at an actual study that was done at a heavy equipment manufacturer where they had 4 compressors that were running, and some pretty significant energy costs. And what they did is used by the way, they used a Fluke power logger to gather information before and after implementing leak detection inspection with acoustic imaging. So before, this is a kind of a map of what's being consumed and when it's being consumed. You can see that each of the different compressors are color coded as far as their energy consumption over time, when they're running, and essentially consumption. So you can see compressor number 4. That's really the one that we're looking at. It was called upon to run quite a bit, and that may have been a backup compressor. So, but what it shows is they're pretty much running their compressors, all their compressors all the time, and this is the before case. After using an II-900 and detecting and fixing leaks, this is what the after looked like. And you can see from the image that really compressor 4, you really almost don't need it. So it truly just becomes a backup compressor. So very significant changes there. And this is just a weekly consumption. So you can see pretty dramatic drop from about 33,000 kilowatt hours down to about little over 24,000. So dramatic. And it also shows a good use of if you have the ability to log before and after, you can show direct energy savings costs. So to summarize, compressed air leaks, gas leaks can be expensive. So it pays to inspect. What we are representing here with acoustic imaging is a better, easier, faster way to perform those inspections, to document it, and also the tools give you the ability to assess which leaks are more severe, so you can prioritize your repairs. I think at this point, Sean, we'll open it up to questions.
Perfect. Well, thank you so much, Dave. So everyone, now is the time for you to take advantage of having an expert like Dave with us to answer any and all questions you may have. So just to send in a question, just please use the chat feature. And please note that if you have any specific product related questions, such as pricing and availability, we really encourage that you visit itm.com. There you're going to find a list of products, pricing, availability, technical specifications, as well as our contact information with all the different ways that you can connect to our technical support staff. We'll be happy to address any and all questions that you may have. Okay, all right, Dave, so we have one so far. So for vibration screening with the Fluke tester, how are we going to know what's good or bad?
Great question, and it's actually it's a pretty common one, one that I've heard quite a bit. The 805 FC, as I mentioned, has some intelligent screening capabilities built into the tool. One is a bearing health assessment, where on a scale, it's making a particular measurement. We call it crest factor plus, but it's really a measure of where is that bearing, rolling element bearing, in the stages of wear, in its life cycle. So it will give you a number which can be trended over time to again see if you have any sharp changes. But there is also an automatic good, satisfactory, unsatisfactory, unacceptable message that's shown. So immediately when you make the measurement, which takes about a couple seconds at a bearing location, you'll get that quick instant assessment. Overall vibration, in the tool we have 37 different machine categories that you can select from, things like centrifugal pumps, belt-driven loads, motors, gearboxes, a wide variety, 37 different categories. What you're loading in then are based on an ISO standard for vibration. It's loading in what is acceptable for that class of machine. So if you do select those on your overall vibration measurement, you're also going to get that same good, satisfactory, unsatisfactory, unacceptable call out immediately when you make the screening measurement.
Great, thank you. And we have Amjad asking, is the acoustic imager intrinsically safe?
Great question. And actually, I would, if I were face to face with you, I'd ask you more about your environment, but I'm guessing you're talking about perhaps class 1, div 1, or class 1, div 2 environments. The answer is no, the imagers are not. However, in many cases, what we found is that because of the ability to detect leaks at much greater distances, then you can see whether you do need to be able to, perhaps get a hot work permit to move into the area or not. You may be able to rule in or rule out that there are leaks occurring in an area that is one of those environments.
Good to know. Can acoustic imaging detect leaks in a hot oil thermal system?
I'm not that familiar with a hot oil thermal system. I think maybe in this case, what if we could do, Sean, if we can maybe capture that, we're happy to look into that a little bit more, and maybe we can get back with you via email. Do we have that capability?
For sure. Joseph, if you could just reach out to us and explain exactly what your application is. Dave and I will look into this and we'll get back to you with all the facts.
Okay.
Thanks.
Yeah, and again, it's for gases. Okay, so again, my knowledge is limited in that type of system, but it's line of sight technology. and it's for gases, either air or other gases. So if you have line of sight, are able to see what it is you're looking for, then you should be able to detect it. It's not for finding fluid leaks, for example, liquid leaks, I should say.
Perfect. And we're starting to run out of time, so we'll try to go through these. Nick is asking, for the acoustical imagers, what is the distance that they are able to pick up partial discharge?
Great. Yeah, you can detect partial discharge at, I think, a max of around 300 feet, roughly. And then also partial discharge is up in a higher frequency range. That features only in the II-910 to have the partial discharge detection, as well as the higher frequency range in order to detect it. But hundreds of feet.
Good to know. See, I'm taking notes myself. This is great. The last question we have time for is, can you use the II-910 to detect SF6 gas leaks?
Great question. Yeah, SF6 insulating gas used in a lot of medium voltage situations, breakers, whatnot, at substations. I would say that it's not the optimum tool. It is not a gas detector, as would an OGI or optical gas imager be. It may find it, but it would have to be a fairly sizable leak in order to be able to make enough noise to be able to detect it. So I think there's better tools, but if you are using that for a variety of other applications, at a plant or substation, power plant or substation, it's something that you can use, but it's not definitive, because the leak rates typically are much lower, than what can be detected with acoustic imaging.
Perfect. So that's about all the time we have, unfortunately, for questions. But any of the questions we didn't have time for, or that you didn't have time to ask, please reach out to us. You can go on itm.com and find all the information there in terms of contacting us. Send us an email, call, chat, whatever you prefer, and we'll be happy to get back to you with any answers you need. So lastly, just to wrap things up, I just want to say on behalf of ITM University, we thank you all for attending our webinar today. We hope you found it very informative and helpful. ITM Instruments is available to assist you in any way. Simply visit us at itm.com for anything you need. Through itm.com, you will have access to the entire list of Fluke products with the descriptions and specifications. You will also find our contact information in order to contact and connect with one of our technical support staff who are able to answer any and all questions you may have. At the end of this webinar, we are going to have a very short survey that we'd like you to complete. Your feedback will assist us in improving and allow us to bring you more topics that are of interest to you. We have upcoming webinars of the next few weeks and months. Please visit the training section on itm.com for a full schedule of the upcoming webinars and topics. Lastly, don't forget that as a thank you for attending our webinar today, your name will be entered in the draw to win $100 for your next online order. The winner will be announced on social media, so please be sure to check us out there. Thank you so much, Dave, for all your help. It was very informative. I myself learned a ton, and I'm sure everyone else did. And we appreciate your time today.
Thanks much, Sean. Appreciate it. Thanks, everybody.
Awesome. Take care, everyone. Have a good day.